Hello and good morning, afternoon, good day, students. We are going to continue marching forward in chapter 17, where on Wednesday we have previously, talked about or brought together our conversation of weak acids and weak bases, along with their conjugate acids and conjugate bases being present in solution at the same time. So on Wednesday, explicitly then, we talked about the common ion effect and how it pertains to weak acid, weak base equilibria. Today now we are going to be bringing back chemical reactions. So we're not just going to be looking at stagnant vessels, stagnant flasks, or beakers that happen to contain some of these weak acids or weak bases. We are going to be mixing acids and bases together, and not just conjugate acids with weak acids with conjugate bases, but we're actually going to be performing chemical reactions here. Different species that will come together to create all new product. And so we're going to talk about the neutralization reaction and also then today introduce what we know as buffer solutions. So here we have some associated pages. If you have not been reading along so far with the material this semester, I would strongly encourage you to do so in chapter 17, because the type of problem that we are going to be working through is very detail-oriented, and there are plenty of steps, not a lot of equations. It's a lot of just knowing the process. So let's get started. Okay, so a review from chapter 9. Chapter 9 being at the end of fall semester when we first talked about neutralization reactions. The question now is what is this again? A neutralization reaction is some kind of double displacement reaction. So we have cations swapping or anion swapping between an acid and a base. So the acid and base component is really what defines a neutralization reaction. We need some acid to neutralize a base or a base to neutralize an acid. Really, they're neutralizing each other. The products then are commonly water and some type of ionic salt. So for example, one very common acid-base example is we take the strong acid of HCl, mix it with NaOH. Here we are taking an acid and a base. We are mixing them together. There's going to be some type of double displacement, so the cations on both species are going to swap places. H plus for the Na plus. What this is going to give us is NaCl, so salt, and HOH, which is just water. So this is an example of a neutralization reaction, right? Anytime we have an acid and a base, they're going to come together, most of the time forming water along with some type of ionic salt. But the double displacement portion of this description is really going to tell you how you can predict what your products are going to be. You're always going to swap your cations for each other. You'll see what products then result. A neutralization reaction from this example then, we can see contains some type of strong acid or strong base. In this case, it had both. Neutralization reactions are the most useful to study, at least for analytical purposes, if it contains at least one strong acid or strong base. So these are the cases we're going to be looking at. If a strong acid or strong base is present, our reaction is going to be a complete reaction. Complete reactions mean that we're going to be looking at stoichiometry again. So here's where everything now is going to come to a head. We have studied in the past, right, chapters 8, chapters 9, strong reactions, or not strong, complete reactions where stoichiometry comes into play, where we're looking at theoretical yields, and we're able to predict that, a theoretical yield using stoichiometry. We have limiting reactant. We also have excess reactants. And all of the calculations for determining theoretical yields, limiting reactants, excess reactants, all of this we learned when introducing stoichiometry in chapter 8 and employed it really the first time in chapter 9 when we introduced precipitation reactions, acid-base reactions, and redox reactions. Here, now we are going to be tying those ideas from before together with our weak acid and weak base chemistry, where if we're looking at weak acids and weak bases in solution, these are not complete reactions. These are reversible reactions. And if we're looking at a reversible reaction, we have to use the ice table method to figure out some type of possible yield, or what reactant do we have left over, all of those questions. We need to look at equilibrium conditions. We can't just assume that there is a complete reaction. So what we're really going to have to be paying attention to is, does your reaction contain a strong acid or a strong base? If it does, your reaction will be complete, and you're going to have to use stoichiometry to figure out a theoretical yield, limiting reactant, excess reactant, whatever it is that you're looking for. If your reaction involves a weak acid or a weak base, it is going to be reversible, and you're going to need to use the equilibrium calculations that we've been working with. We're going to be looking at cases now for the rest of chapter 17 where we are going to be mixing acids and bases together. So really what it's going to come down to is just looking at your reaction step by step. What is happening in the beaker? What reaction is occurring? What is its nature? And what form of calculation, either stoichiometry or ice, are you going to have to perform to actually figure out the required information from this reaction? Okay, so let's just jump into looking at some example problems. Okay, so the first example we're going to look at is the neutralization of a weak acid, HF, with a strong base, NaOH. We are going to be adding 0.25 moles of our strong base to the previously mentioned 1 molar solution of HF. So previously mentioned means that we talked about this solution on Wednesday. It was a hypothetical solution that had a pH of 1.57. On Wednesday, we added some F- to it. We looked at what happened according to the common ion effect. What we're doing now is we're just starting with another, hypothetical flask of 1 molar HF. And we're going to throw into it 0.25 moles of NaOH. And we're going to see what happens. And by see what happens, I mean, assuming no volume change, we're going to find the pH afterwards. Okay, so the assuming no volume change is going to be very important here. Actually, next Monday, we're going to look at cases when the volumes change, when we're going to actually have to take that into account and what it means. But for now, we're going to keep the calculations quote unquote easier and assume that there is no volume change. Okay, so the reaction vessel, this flask, contains 1 molar HF and now 0.25 moles of NaOH. If our goal is to figure out what's the pH after a neutralization reaction has occurred, well, we'd probably start by writing out what our actual chemical reaction is. We have HF, aqueous conditions. We are adding some NaOH to this, also with aqueous conditions. What are the products going to be? Well, we're going to perform a double displacement, so we're going to take this H plus and swap it for this Na plus, giving us NaF, aqueous, as well as some H2O in liquid form. This reaction, because it contains a strong base, is a complete reaction. Complete. Meaning that any calculation pertaining to the consumption of our reactants or the generation of our products is going to have to use stoichiometry. So what are we looking for here? Well, we're trying to find what is the pH after this reaction is done. And from what we know of acids and bases, there needs to either be an acid or a base in solution, some initial concentration, some either final or theoretical yield or equilibrium concentration, that we can actually look at some H3O plus or OH minus and calculate a pH. So in other words, what we need to do is figure out, after this reaction is complete, what is the excess reactant gonna be? Are we gonna have some excess weak acid left over, or are we gonna have some excess strong base left over? In addition, in observing the products, we see that we have some sodium fluoride. We've seen this before. On Wednesday, we looked at the importance of acknowledging the conjugate base, or, conjugate acid, as it's present in solution and how it can also affect the pH. For this reason, we also need to know what is the theoretical yield specifically of our NaF, since we know that its existence is going to influence the pH in some way. So let's figure out what our excess reactant is first, or if this is actually a complete stoichiometric reaction. So we know that we are adding 0.25 moles I'm just going to gather some information underneath each of the compounds so we can organize a little bit. We have 0.25 moles of sodium hydroxide, and this is going to be mixed with a 0.1 molar solution of HF, 1 molar solution of HF, and we have 1 liter of this. Now, if we have a 1 molar solution and 1 liter of that 1 molar solution, what this means is that we actually have 1 mole of HF. So we're mixing 1 mole of HF with 0.25 moles of sodium hydroxide. Let's figure out which one of these is the limiting reactant. Well, we can see that both of these solutions are being mixed together in a 1-to-1 ratio, right? We're mixing 1 mole of our hydrofluoric acid, and according to this 1-to-1 ratio, we would need 1 mole of sodium hydroxide to complete this reaction, to completely neutralize our HF, to completely get rid of it. But we don't have 1 mole, we have 0.25 moles. The 0.25 moles will be completely used up. We can assume that our sodium hydroxide is our limiting reactant. And we've observed, that this is going to be the limiting reactant just through common sense by, observation, that because this reaction is a 1-to-1, when completely balanced, we would need to have a 1-to-1 of the molar amounts present. We do not have that, making sodium hydroxide the limiting reactant. Because it is the limiting reactant, all 0.25 moles of our sodium hydroxide are going to get used up in this 1-to-1 reaction, 1 mole of sodium hydroxide being converted into 1 mole of our sodium fluoride, meaning that we're going to generate 0.25 moles of sodium fluoride, right? This is going to be our theoretical yield calculation. This should look familiar, right? We learned how to do this back in chapter 8. If you're feeling a little rusty on this kind of calculation, please go back, review those chapter 8 notes or the chapter 8 material in the textbook, my lecture slides, whatever you have available to you. If you feel like this calculation was very mundane, awesome. That's a good place to be. You don't necessarily have to go back and review chapter 8. So we have now generated 0.25 moles of our product of interest. This does not quite, though, answer the question of what is our excess reactant. I mean, we know that the HF now is going to be our excess reactant, but how much is actually left over? The amount that's left over is going to also contribute to what the final pH is going to be afterward. Well, if we had 1 mole, the question is how much of this got used up? Since this reaction is a 1-to-1, right, 0.25 moles of the NaOH, again, reacts in a 1-to-1 with our hydrogen fluoride. This calculation might also, NaOH, that got a little muddled, a little sloppy. This calculation may seem unnecessary, but I want to be explicitly clear about how the stoichiometry from before is connecting to our ideas now. So I'm not going to continue doing these calculations, but at least for this first round, yes, I am showing the stoichiometry. We have used 0.25 moles of HF. This is the amount that has been neutralized in the reaction and is now gone. We have lost this much, meaning that we should have our starting amount, 1 mole, minus the amount that just got neutralized, and this will tell us how much we have left over. In other words, a 0.75 moles of HF is left over. As the reaction has progressed, our limiting reactant has gotten entirely used up. We have some excess HF, and we have generated some sodium fluoride, which, as we saw on Wednesday, is also going to influence our pH in some way. So now that the neutralization reaction is complete, we can actually answer the question, what's the pH afterwards? Well, in order to figure out the pH, we now know what species we have left in this flask. This flask is now going to contain some HF as well as some NaF. And these are the substances that are going to be used to find our pH. Sodium hydroxide is completely gone. Product and leftover reactant are all that remain. In other words, if we're trying to break down this problem, step 1, which we have just completed, is the neutralization itself. Step 2 is what's left over. What is left inside of that flask to actually calculate pH or pOH or whatever is being asked of you. Neutralization is done. Let's actually calculate what's the pH. All right, if you haven't written down this information yet, then please pause the video. I'm going to clear up the slide now. All right, so we've left off with there being 0.75 moles of HF inside of our flask, as well as we have just generated 0.25 moles of the sodium fluoride. Well, whichever direction we decide to write our balanced chemical equation, either our weak acid is interacting with water, generating some conjugate base, or our conjugate base is present in water, or I should say weak base, and is generating some conjugate acid. Technically, it doesn't really matter. I like to keep my perspective from the weak acid. That tends to be kind of our convention. So I'm going to write out the balanced chemical equation for what is happening, how these two things are interacting together in aqueous conditions, right? Water is all around us. We have to acknowledge that there is some type of dissociation occurring in aqueous conditions. This is a reversible dissociation, meaning that we're going to have some F- afterwards, as well as some H3O+, but this is going to be reversibly reacting, coming back together to regenerate some of our initial reactants. We know how much there is of each of these substances initially, and if we want to find pH, right, we're going to have to look for some equilibrium condition. What is the concentration of our H3O+ once equilibrium has been reached? Assuming that as soon as the neutralization is finished, we're starting this second reaction now in solution. We have 0.75 moles of HF divided by 1 liter, and we have 0.25 moles of F- also divided by 1 liter. No H3O present initially, right? There was just a neutralization reaction. A bunch of NaOH was added. So it's not like there was a bunch of H3O+ floating around. Now we are going to have to generate some. There is a change as the reaction is shifting from reactant to product, and our equilibrium conditions, the 0.75 minus X, 0.25 plus X, and X are what we're going to be solving for. We need to know what our X is. Since our X is equal to the equilibrium concentration of the H3O+, that's going to be really what we are looking for. Now, there's no Ka explicitly listed in this problem, but since this is a reference to a problem from Wednesday, previously mentioned, means that our previous information is still going to be viable here. The Ka was previously told to us, which is equal to a 7.1 times 10 to a negative 4. This Ka we can set up in an equilibrium expression, as we have been doing and will continue to do, at least for the rest of this week. Divide by our reactant concentration. Now, if we insert all of our information, that we've laid out, I've kind of expanded my ICE table a little bit more than what I should have. Our F- concentration is a 0.25 minus X. H3O+ concentration is a plus X. And we're going to divide by the HF concentration, which is a 0.75 minus X. All of this being equal to the Ka of 7.1 times 10 to the negative 4. Now, I'm jumping over the math here. Please fill in the blanks. The X that I found in rearranging and solving for our X is a 0.0021 molar. I went through the process of using the quadratic equation, solving my math algebraically that way, but here is the X value that I have calculated. Now, this X value is equal to the concentration of H3O+, meaning that we can go ahead and use it to solve for the pH by taking the negative log of this value. And the pH of our solution, right, our HF solution that we added some NaOH to, neutralized a little bit of it, our pH ends up being equal to a 2.68. Whew. All right, so a lot of math. Step 1, set up your neutralization. What is it that's being neutralized? What do you have in your flask? What do you have in your beaker? Step 2 is, now that you know what's in your beaker, what either reversible reaction or equilibrium is occurring between your weak acid, weak base, whatever is all present. This information then you can lay out. Again, you could have set this up as a weak base dissociation with water. If you use the Kb for F-, which we also learned what it was on Wednesday, you could have also solved the problem from that perspective and you would have gotten the exact same pH. The math just would have looked a little bit different. The takeaway message here is that we had a flask that initially had some HF inside of it. Its pH was 1.57. This was information given to us for reference. We added some base to it, neutralized some of our acid, and now suddenly we have a solution that has HF and NaF- inside of it, which its pH has increased, right? It's become more basic to a 2.68. Okay. We could have predicted that this would happen. In fact, it makes sense, right? If you add base, your pH should become more basic. But now we actually have the means to quantitatively explain why does that happen? Why does your pH become more basic? It's not just because you're adding base, it's because you're neutralizing acid. It's because you're adding some conjugate base in the process. Okay, let's look at another example. Since this type of problem is pretty beefy, let's look at another example. The second example is very similar, except we are not just looking at the neutralization of a solution that is solely comprised of weak acid. We are looking at a solution of 1 molar HF, and we have added that 0.5 moles of sodium fluoride. We have present a common ion solution, of which we also studied that on Wednesday. The pH that we found of the solution was slightly more basic. It was 2.85. Now the pH shift is going to, again, since we're neutralizing with a strong base, we're going to predict that this is going to become more basic, but we want to know exactly how much more basic is it going to get. What is the pH going to be after you add 0.25 moles of sodium hydroxide to this solution? So we're going to start this problem in the exact same way that we started the previous problem. Step 1, we have to know what is our neutralization reaction that is occurring. We are adding strong base, which means that your neutralization is going to be a complete reaction. Now, bases always interact with acids. That's what neutralizes, right? Base neutralizes acid. So our reactants in this complete reaction are going to be our HF, the acid that is present in our solution, as well now as our strong base that we are adding. We already know what happens when you add your conjugate base, your NaF, into a solution of HF, right? We studied that on Wednesday. We know that there's no neutralization that's happening. It's just a rebalance of your equilibrium. Here, we have strong base, which means you are going to have a complete reaction going straight from reactant to product. The reactant to product that we're going to expect is sodium fluoride and water. Right, neutralization of your weak acid to generate some more conjugate base and water. Now I'm going to gather the information as I did previously. We have 1 liters. Again, we're assuming that there's going to be no volume change. We have a 1 liter solution for simplicity's sake. Because we have 1 liters of a 1 molar HF solution, that means that we are starting with 1.0 moles of HF. The amount of sodium hydroxide we're adding is the same as in the previous problem, 0.25 moles. Now I'm going to teach you guys a really nifty shortcut, and the shortcut that I'm going to be showing you here, the shortcut, specifically the shortcut to the stoichiometry piece, this neutralization piece, the shortcut only works in a straightforward way if your reaction, your complete reaction, is all in a 1-to-1. In other words, if all of your stoichiometric coefficients in front of everything are a 1, which is exactly what we have here, this nifty little shortcut is going to work. I feel like you guys have been through the ringer with stoichiometry. You've been seeing some really intense, complicated math. You can handle a little bit of a shortcut when it comes to stoichiometry. What's really nice about this shortcut to stoichiometry is that it does all of your calculations for you. If you can identify what your limiting reactant is, which is really easy if everything is in a 1-to-1, because it's going to be the smaller of the two reactant values. In this case, sodium hydroxide, again, is going to be our limiting reactant. We're going to be able to calculate what our excess product, our excess reactant is going to be, and what the theoretical yield of our product is in one fell swoop. What I'm going to do is add the amount of our conjugate base that we have present also here. The limiting reactant, since we know by definition, gets entirely used up in the reaction. 0.25. We're losing 0.25 moles of sodium hydroxide, meaning that once the reaction is complete, we will have no sodium hydroxide left over. We are also, because this reaction is a 1-to-1 with HF, going to be losing 0.25 moles of HF, giving us 0.75 moles of HF left over. As the reaction progresses and we are creating product, we are going to be gaining 0.25 moles of our NAF, giving us 0.75 moles of NAF then once the reaction is complete. We can see here that we have 0 of our limiting reactant left over. We have a quick, simple way to calculate what is the amount of our excess reactant. And we have a really nice way to calculate our theoretical yield. And all of this is without having to explicitly set up our stoichiometry, because everything, again, is in a 1-to-1 that we can see here. We're just going to subtract the same molar values or add the product just across the board. Okay, so our neutralization reaction is complete. We know how many moles of excess reactant we have left in the flask. We know how much of our conjugate base is also present in the flask. And from here, the problem now becomes the exact same second step from the previous problem. We now have something that is in the flask, right? If the question is, what's in the flask? How's it interacting with water? Now we can set up a reversible reaction with water to solve for the pH that is still existing inside. We know that we have this much, 0.75 moles of HF and 0.75 moles of NaF. So let's set up that ice table that we had. How do we know, again, that it's an ice table? Like, why are we always doing these ice tables? Well, we're doing these ice tables, again, because this reaction, this interaction between the weak acid and water is reversible. The products that we are generating can come back together to create reactant. Since we have a weak acid, right, our HF is a weak acid, F- is a conjugate base, we have to acknowledge this reversible nature, right? That's the whole point of everything that we've been doing since chapter 15. So we have some initial concentration, some change in concentration, some equilibrium concentration. The HF concentration initially is going to be 0.75 moles, all divided by 1 liter. The F- concentration is 0.75 moles, also divided by 1 liter. Water, who cares? H3O plus, none of it initially, and we're going to see now with the change as we rebalance and lose some reactant, gain some product, what the new 0.75 minus X, what the new equilibrium concentrations are going to be, 0.75 plus X and X. The Ka for this reaction, again, because it is a previously prepared reaction, the Ka is going to be the equilibrium constant of the weak acid that is of interest to us. Our Ka is equal to that 7.1 times 10 to the negative 4. And the concentrations we can plug in to our equilibrium expression in much the same way that we have. Product concentrations in the numerator, all divided by reactant concentrations. So 0.75 plus X is all times X. This is divided by 0.75 minus X. Now again, I'm going to jump over the complicated math since the algebra here is not the new lesson, right? The new lesson is how does neutralization affect pH? How do we have to take into account the addition of these strong acids and strong bases? Our x, in solving the problem that is laid out before us, this second example, the x is equal to 7.1 times 10 to the negative fourth molar. This x, much like before, is equal to the equilibrium concentration of the H3O+, meaning that we can find a pH right away from this by taking the negative log of our concentration. The pH now we can find is equal to 3.15. Now, as was predicted, since we are adding a strong base, we expected our initial pH, that was 2.85, to shift basic. And that is exactly what we saw here, right? It shifted from 2.85 to 3.15. How curious, though, it is that a solution in the previous example was 1 molar HF. We added some strong base, and we saw a shift towards the basic by a certain magnitude. Too far. Just to go backwards, the shift that we saw from 1.75 to 2.65, the difference here, was equal to a change of 1.11. Right, we saw a pH shift of what a pH, again, as a reminder, scale means is every digit that we change means that our pH has shifted by a factor of 10, like a concentration factor of 10. So we've literally gone, from a solution that had a certain acidity to 10 times the basicity just by adding 0.25 moles of our sodium hydroxide. In our second example, where the pH was initially a 2.85, this we found yesterday, to a total value of 3.15, this is a difference that is equal to 0.30. We added the same amount of base, 0.25 moles of sodium hydroxide, but we got 1/3 of the shift, 1/3 of the magnitude change. The reason being is exactly because of the presence of the sodium fluoride. So if you're tired of doing math, I am also tired of doing math. Let's do a bit of a qualitative inspection of what this observation is, like what it means, and also how it can give us another shortcut in the math that we have to do when it comes to finding pH of solution. The type of solution that we just studied in our second example is known as a buffer solution. This, by definition, is a solution that contains a certain amount of weak acid or base. So it could be, HF, like what we just studied, but also it has its conjugate present. So a weak acid in solution will be with its conjugate base, or a weak base will be in solution with its conjugate acid. The result, though, of both of these species being present is that you're going to be working with a solution that is going to be more resistant to pH change due to the common ion effect. In our previous example, we saw less of a pH change because the conjugate base, that F- was present. If F- is present, according to our equilibrium expression, as we have our HF interacting, dissociating, creating some F+, if we have an increased amount of our F+, what this means is that we are going to be resistant to changing or neutralizing any of this HF, right? If we neutralize a certain amount of this HF to create some F-, because we already have F- present, according to our dissociation reaction, we're going to be regenerating some of this HF that was previously neutralized by the strong base. Right, so we can use this as a qualitative description as to why the pH did not change as much in our second solution. In the chart or illustration below, we can kind of see a diagram representation of what it was that I just said. If we have some type of buffered solution, so here we have acetic acid present in solution with the acetate ion. If we were to hypothetically add some H3O+, yeah, we're going to be neutralizing a little bit of the CH3COO-, that acetate ion, and we will be generating some of this acetic acid, but we can see that there relatively wasn't that much of a change from the conditions that we started with, since both of them were present in a like pretty significant or marginal amount. If we were to add some of our weak base, we would see, again, there's a little bit of a difference here. We're shifting away from that, equal concentration, but it's not so significant of a difference that we're going to see a significant difference in the overall H plus concentration. Because really, again, that's what connects to pH. pH is a representation of the H plus concentration. And so if we're going to be neutralizing the weak acid or weak base that's present by adding some strong acid or strong base, if we don't see a huge shift away from our initial conditions, we're not going to see a huge shift in the corresponding pH. Buffered solutions are incredibly important. Buffered solutions are what keep you and me alive. If you've ever wondered, again, why is it that like your stomach acid doesn't just like eat through your entire body? Why is it that you're not just like a puddle of jello, since we have pH differences all across our body? It is because of buffers. The solutions inside of our body contain weak acids and bases as well as the conjugate ions readily present. And these conjugate ions are what keep our pH levels stable. It's what prevents us from neutralizing ourselves as we exist. Okay, so how do we know that a buffer is a buffer? Since we, let's say for instance, in the first example, we had some HF, there was no conjugate base present, but through the neutralization reaction, we created some of our sodium fluoride. Was that a buffer? How do we know? The buffer capacity, or the capacity with which a solution can be considered to be a buffer, is according to the definition below. If your conjugate base to weak acid proportion is somewhere between a magnitude of 10 and 1/10, you're working with a buffer. You are working with a solution that is going to be resistant to pH change. So our buffer capacity definition is the greater the concentrations of your weak acid and conjugate base, the more of both of these you have, the more resistant to pH change your solution will be, the more buffered your solution will be, because it's going to take more and more of your strong acid or strong base to neutralize your weak acid or conjugate base. If you have a ton of this present, there's not going to be a whole ton of neutralization going around. Your solution is going to be buffered at a specific pH, and your system will be stable. All right, so since buffered solutions are so resilient, because they are so resistant to pH change, two scientists by the name of Henderson and Hasselbalch decided to see if there was a way to more easily calculate, what are the pHs of these solutions, since they are so resilient to change. The Henderson-Hasselbalch equation is what they came up with. This is used to calculate the pH of a buffered solution in which the equilibrium concentrations of your acid and your conjugate base are known. And because this is a buffered solution, your equilibrium conditions will be similar to initial conditions. There's not going to be a lot of a change here. This is exactly why we can use the Henderson-Hasselbalch shortcut. If your solution is not a buffer, no Henderson-Hasselbalch equation for you. Your solution must be a buffer. If it is not a buffer, you will not get the correct pH. If your solution is not a buffer, you will have to go through all of the ice calculations as we have been learning. If your solution is a buffer, though, we can use the equation that is outlined here, where your pH is going to be able to be calculated by taking the pKa, which is equal to the negative log of your Ka, and you can add the log of the concentration of your conjugate base divided by the concentration of your weak acid. All right, so let's use the Henderson-Hasselbalch equation and readdress the previous problem that we have studied. All right, since we have now acknowledged that that solution was a buffered solution, how much easier would the problem have been if we had known the Henderson-Hasselbalch equation ahead of time? So here we have the rewording for the problem. It is the exact same problem. In order to solve the problem, we will have to go through our first step, the first step being the neutralization reaction that has to occur. Neutralization. Since we have a strong base present, the strong base will react, right? Strong base must neutralize. We can think of this thing as the Terminator. It is on the hunt, and it will neutralize any, in this case because it's a strong base, it will neutralize any weak acid it comes into contact with. So the weak acid we're working with is the HF again. It is interacting with the sodium hydroxide. It's going to neutralize, as we have seen. Again, this calculation is the exact same first step. We started with our 1 mole here, 0.25 moles of our sodium hydroxide, started also with 0.50 moles of our sodium fluoride, subtracting out our limiting reactant from the reactant side, adding the generation of the product to the product side. And again, what this gives us is a 0.75 mole of HF and a 0.75 mole of NaF. In order to use the Henderson-Hasselbalch equation, our values have to be in concentration units. Since again, our volume is 1 liter, what this means is that we have 0.75 molar HF as well as 0.75 molar NaF. The second step, though, is where we are going to vary now, because we acknowledge that we are working with a solution that is a buffered solution, and we can see that because we have equal values, equal concentrations of our HF and our NaF, right here and here. What this symbolizes is that we are working with a buffer. And whatever the concentration change is going to be very, very small. We are not going to get a huge shift away from the concentration initially. So what this means is that we can use the Henderson-Hasselbalch equation here. And our Henderson-Hasselbalch equation, just to clear the slide, is equal to, or is a means to calculate pH, which is equal to pKa plus log of the concentration of A minus, all divided by concentration of HA. The negative log of our Ka value, the negative log of the Ka is 7.1 times 10 to the negative 4, plus the log of 0.75 molar, all divided by 0.75 molar. Our A minus, which represents our conjugate base, in this case is going to be our sodium fluoride concentration. Our HA, or our weak acid, is going to be our HF concentration. They're both equal to 0.75, but just to be explicitly clear, that's where I'm plugging the information in. Well, 0.75 divided by 0.75 is equal to 0. Meaning that, or 0.75 divided by 0.75 is 1, meaning that if we take the log of 1, we get 0. Sorry, want to make sure I'm not like saying incorrect mathematics statements because my brain's jumping steps. The pH of our buffered solution is equal to the negative log of our Ka, the negative log of 7.1 times 10 to the negative 4, which is exactly what we calculated before, 3.15. That was so much easier than having to go through all of the ice table calculations, the quadratic formula, solving for x, plugging x back in. If you're working with a buffered solution, this is how easy the math is going to end up being. Okay, but you do have to make sure, again, you're working with a buffer. You might not be told in the wording of the problem that you are working with a buffer, but if you inspect the wording of the problem and ask yourselves, am I working with a buffer here? Am I within, or are my initial concentrations, are my concentrations of the weak acid and the weak base after a neutralization reaction within the magnitude of 10 from each other? If so, you're working with a buffer and you can take this really handy shortcut. All right, again, working with buffers or acknowledging buffers is incredibly important for anyone who, uses or looks at chemistry as a way to appreciate life as it has developed on Earth. Working with, though, buffered solutions is also very handy when working with any type of biochemical setup. I know a fair number of you in class are interested in the biochemistry major, or at the very least are interested in biochemistry as a topic. One really neat study or molecule to study biochemically is hemoglobin, right? It is very widely studied. That is what the illustration is here. We have this huge protein structure, and the protein itself is only stable, or only does its job, is what I should say, at a pH of 7.4. Your blood is ever so slightly basic, but if the pH in your blood becomes acidic, your hemoglobin no longer wants to bond to O2. If your conditions in your blood, your pH drops to less than 7, hemoglobin really likes bonding to carbon dioxide, which is a problem because carbon dioxide, if it gets stuck in your blood, is going to cause you to asphyxiate. So if you want to study hemoglobin in a way to understand what's going on in the human body, you need to make sure that your solution has a pH that is 7.4. If your pH is too low, you're going to get incorrect binding. If your pH is too high, the protein itself breaks. And so you're not going to get a really good, result or study or whatever if you're working with hemoglobin if your pH is off. So let's learn, how do you intentionally prepare a buffer solution for the cases where you are going to be working with biochemical molecules or whatever your study might be. So here we have an example laid out to create a phosphate buffer. Phosphate buffers are really common buffers in biochemical labs. Phosphate in this problem specifically we're going to be using to create a buffered solution that has a pH that is equal to 7.4. So our question is, what mass of K2HPO4 are we going to have to add to a solution that is 100 milliliters total, that currently is a 0.1 molar solution of H2PO4 minus. The Ka of this molecule is present here, in order to create that buffer. Like, how much of the hydrogen phosphate do we have to add to the dihydrogen phosphate to actually create a useful buffer? Well, the key word in this problem is buffer. Anytime you see the word buffer, you got to be thinking to yourself, Henderson-Hasselbalch, because this is going to be saving you a world of hurt in the calculation category. When I say that, I mean we can use the Henderson-Hasselbalch equation, or pH equal to pKa plus log concentration A minus divided by concentration HA, in order to figure out the solution to this problem, or at least as a first step in the solution to this problem. Because our question is, how much of the how much of the conjugate base, the A minus, do we have to add to the acidic solution in order to create a buffered solution with a very specific pH? So in other words, in the Henderson-Hasselbalch equation, we are looking for the concentration of A minus. Since we know the volume of our solution and we know the formula of the compound, we can figure out what is the exact mass that we're going to have to add. But first we need to figure out what's the concentration at equilibrium that we need to actually make the buffer. All right, so we have a pH that is given to us, 7.4. We have the Ka of the weak acid that we're going to be considering. So this is a negative log of 6.2 times 10 to the negative 8. We're going to be adding the log of our unknown, which is our A minus, all divided by the concentration of our weak acid, which is in this case a 0.10 molar. Now, how did I know that the H2PO4 minus is the weak acid in this case and not the conjugate base, right? Because there's a minus sign here. Well, there were two hints. The first hint is that we are given a Ka that is directly after the molecule. A means acid. Pretty, easy to tell there that the H2PO4 minus, the molecule that preceded it, is going to be an acid. The second hint, or the second clue, is that the H2PO4 had one more hydrogen than the HPO4, right? If we get rid of this K2, this whole thing is going to have a 2- charge, meaning that it has lost one of its hydrogens. So that's what tells us that this molecule right here is the A-, or the conjugate base of the weak acid that we are going to be studying. So from here, it's going to be a matter of algebraically rearranging and solving for what our A minus is. So let's do that math. We have a 7.4 is equal to the negative log of our Ka. What this value comes out to be equal to is 7.21. This is going to be added again to the log of our A minus, all divided by 0.10 molar. We can subtract the 7.21 from each side, minus 7.21. What this gives us, go up here, is a value of 0.192 equal to the log of the concentration of A minus, all divided by the concentration of our HA, which is 0.10 molar. Now, if we want to get rid of this log, we're going to have to raise both sides into the exponent of 10. So 10 to the 0.192 gives us a value of 1.56. This is going to be equal to the concentration of A minus, all divided by 0.10 molar. If we multiply this 0.10 molar up, what this gives us is a concentration of A that is going to be equal to 0.156 molar if we want to create a buffer with a pH that is equal to 7.4, if we are working also again with the phosphate system. So from here, right, because we've set up and we've found our concentration of A minus, this is not exactly what was asked of us, right? We're asked to find a mass. Well, how fortunate for us then that the second half of this problem is very similar to a problem that we've seen either in lab before or chapter 8, chapter 9. We have a concentration which is in units of mole per liter. We also have a liter, and we can find a molar mass of the K2HPO4 to convert our molar value into grams. So our concentration of A minus, just to rewrite that, is equal to 0.156 molar, which is equal to 0.156 moles per liter. We want to get or use this information to figure out what this value is going to be in grams. Well, if we start with a certain volume amount, which we know how much solution we have, we know what that volume is, 100 milliliters is equal to 0.100 liters. And we can take that value and multiply it by our concentration, the 0.156 moles per every 1 liter, cancel out our liters via dimensional analysis to find 0.156 moles, or 0.0156 moles. We can take this and multiply it by the molar mass of our K2HPO4. The molar mass of this value, right, by observing the periodic table, adding all of the pieces that we need together, 2 potassiums, 1 hydrogen, 1 phosphate or phosphorus, and 4 oxygens, gives us a value of 174.2 grams per mole. Now we can take our molar value, multiply it by 174.2 grams per every 1 mole. The moles cancel out according to dimensional analysis, and this gives us a final value of 2.712 grams of K2HPO4 that must be sprinkled into our 100 milliliter solution of 0.1 molar H2PO4 minus, and we will have a buffer that is at a pH of 7.4, a solution at that particular pH that is going to be resilient or resistant to change and could be used for any type of either biochemical study, analytical study, inorganic study, whatever the study is that you're working with. If you wanted it at a pH of 7.4, here's how you make it. All right, and that's gonna be where we call it a day. So believe it or not, in the textbook, despite everything that we have talked about, we only have 1 section review set of problems, and all of these 3 problems correspond to buffered solutions. So the buffered solution type of problem is a combination of neutralization reaction problem with either a weak acid, weak base system or a common ion weak acid conjugate base system. So be watching out for all of those pieces. Again, the questions that you're going to be asking yourself is, what is the neutralization that is occurring, and then after the neutralization is complete, what's in the beaker. What's in the beaker is going to give you the information that you need to either set up some type of reversible reaction or equilibrium system, or if that's not even necessary, then you can find your pH after the neutralization has finished. All right, no additional announcements. Be looking out for an email or an announcement on Blackboard specifically if I haven't sent it out by the time this gets posted as to what's going to be happening with the final exam. Since that is just around the corner, I want to make sure that we're all on the same page as to what my expectations are. I haven't set that announcement as of recording this lecture, but it should be coming soon. Other than that, no additional announcements. So unless you have any questions, which you can shoot my way via Discord or email, class is dismissed.